Okay, we come back. The last question I have for you today is something called an open feed water heater. An open feed water heater. So in a power plant, the feed water is what is used to put into a boiler, feed through the boiler to turn into steam that goes into the turbine that turns the turbine blades. It's called the feed water. It makes sense for you to, before you put water into a boiler, to make it warm. I mean, if you're putting boiling water on your stove, you want to have it, if you put ice cold water on the stove, it's going to take longer to boil, take more heat to boil it than if you had warmer water. Same thing goes with the power plant. You want to feed, you want to heat that feed water to go into the boiler. And you'll talk in Thermo 2 about how we do it. I'm just going to show you the open feed water heater right now. Open feed water heater is going to have a flow coming in here at 1, a flow coming in here at 2, and it's going to come out a flow at 3. It's basically a contact heat exchanger. What's going to happen is you're going to have a colder stream, so state 1 is going to be at a pressure 1 of 3 bar and temperature 1 is equal to 36 degrees Celsius. State 2, well, it's also going to be a pressure of 3 bar, but it's going to have a quality here that's equal to 92%. And state 3 is also going to be a pressure 3 is equal to 3 bar, and it's going to be a saturated liquid. Okay. We're going to take these feed water heaters and we are going to insulate them like crazy. We do not want any of the heat that we have having from a mixing to escape. If you go to ever go to a power plant, if we ever allowed to go to a power plant again, see these big things look like big Chipotle burritos. They're big heat exchangers. And there's the open feed water heater. There's closed feed water heaters and open feed water heaters. Closed feed water heaters are non-contact heat exchangers. Open feed water heaters are mixing up streams together. They're like your bathtub. You have a cold water, you put hot water in there. Okay. What we want to do here is we want to find out, for this open feed water heater, we want to find out what is the entropy generated. How much entropy do we generate just by running this open feed water heater? Okay. So we look here and we start saying, all right, I've also given this information here that mass flow rate of 3 is equal to 80 kilograms per second. Okay, I know that mass coming out of this is 80 kilograms per second. I don't know anything about the mass coming in. I can't say that it's 40 kilograms per second at 1 and 40 at 2. I just can't split them up like that. That's just not a thing. Okay, I can't do that. So I have to figure out a way to determine how much mass flow rate is in 1 and 2. Because if I want to find sigma dot, my equation is going to be ds cv dt is equal to the summation of the heat transfer rate and the temperature at which that heat transfer rate occurs, plus summation of m dot n s n minus the summation of m dot xting s xting plus sigma dot. Okay, we know this thing is going to be running at steady state, or we're going to assume a steady state. We know it's running with no heat transfer. So we're going to have 0 is equal to m dot 1 s1 plus m dot 2 s2. That's the two flows coming in, minus m dot 3 s3 plus sigma dot. Okay, I want to find this. I want to find sigma dot. I have enough information, 2 things in each thing, to set the state. I can set state 1 and 2 and 3. But I only know mass flow rate 3. So I have 2 unknowns here. And the typical thing students do is say, well, if it's 80 kilograms per second, it's got to be 40 and 40. But that's not true. It's not true. We have to go and find what that answer is. And since we don't have enough information in this law to help find that, we have too many unknowns here. Let's go to the first law. That's our other situation that we can use. Okay, so the change in energy of the control volume with respect to time is equal to Q dot minus W dot plus the summation of mass flow rates in times my enthalpy in minus the summation of mass flow rates exiting times the enthalpy exiting. Notice I've gotten rid of the kinetic and potential energy terms already. I'm tired of those terms. I know it's not there. There's no velocities given. I'm not going to deal with them. Okay, I'm going to save myself some digital ink and not put it in there. Okay, kinetic and potential, steady state and no heat transfer is what we have here. And so we also have it's a heat exchanger, so there's no power occurring there. So we got 0 is equal to m dot 1 h1 plus m dot 2 h2 minus m dot 3 h3. Again, here we can set all these h1, h2s, and h3s, and we know m dot 3, but we're still left with two unknowns. We're still left with two unknowns. So whenever we had three unknowns to start with. This equation has two unknowns. You know if you have three unknowns, you need three equations. You learned that back in algebra. Three equations, three unknowns. What is our third equation? Our third equation is continuity. The change in mass of the control volume with respect to time is equal to summation of the mass flow rate in minus the summation of the mass flow rates exiting. Okay, steady state. 0 is equal to m dot 1 plus m dot 2 minus m dot 3. Okay. What we can do here is we know that m dot 3 is equal to 80. So what did I do in my thing? I said 0 is equal to m dot 1 plus m dot 2 minus 80. Or I said that m dot 2 is equal to 80 minus m dot 1. Okay, now if I plugged this in, here, now I have only one unknown. Okay, my equation is 0 is equal to m dot 1 h1 plus 80 minus m dot 1 h2 minus m dot 3 h3. Only unknown I have here is m dot 1. Only one. Okay. Now, I'm going to just give you the properties. Okay, we've gone through this. This is going to be the first property up here. This is going to be a liquid. We're going to use liquid approximation. H1 is 150.86. S1 is equal to 0.5188. This is kilojoules per kilogram. Kilojoules per kilogram Kelvin. With the quality equation you have for state 2, I'm going to tell you to do the quality equation here. We're not going to practice that in this lecture, but this is going to be 2552.17 kilojoules per kilogram. S2 is going to be 1.6718 kilojoules per kilogram Kelvin. Okay. Saturated liquid, pretty easy. We can look those up directly. So saturated liquid properties, H3 is going to be equal to 561.47 kilojoules per kilogram. S3 is going to be equal to, what I have here, 1.6718 kilojoules per kilogram Kelvin. Okay. I want you not to just accept. I want you to look these up yourself or calculate these to yourself. If you have difficulty here, we're going to have, these should be second nature by now. You should be like, I can set these states. If you're struggling with how to set these states, exam 3 is going to be, even with the extended time I'm giving you, it's going to be trouble because you're going to set a lot of states. You're going to have to set an entropy and an internal energy or enthalpy on almost every problem. And if you're struggling with that and that's taking you some time, if you don't know how to exactly do it, that's precious time. So please work on this and check what you know here. Okay. So what does this give me when I do this? It's going to give me 0 is equal to m dot 1 times 150.86 kilojoules per kilogram plus 80 minus m dot 1 times H2, which is going to be 2552.17 kilojoules per kilogram minus m3, which is equal to 80. This is going to be kilojoules per second times 561.47 kilojoules per kilogram. And so if our best thing now to do is just do some algebra and find out what the answer is here. Okay, so if we do that, and I'm gonna skip it a little bit. I'm not going to do all the algebra here. M.1 is going to give me 66.32 kilograms per second, and I know that M.1 plus M.2 has to equal 80, so that means M.2 is going to equal 13.68 kilograms per second. Okay, that is what we need to do here. Now, where I want you to take over now is, now we got to go back here to this first law. Now that we know M.1, M.2, now I want you to fill out this equation here. I want you to find sigma dot with this equation. You now know M.1, you now know M.2, and we found all the entropies. Now your job is to find out what the answer is.
I must know the answer.
You must know the answer, Jake, and so you can do this. You can do this yourself. You can just plug them in, and you can find out what the answer is. It'll be awesome. You will love it.
Yes.
Yes, you can. Yes, you can, Jake. So the final top hat question, sigma dot is equal to this value. I'm going to ask you to give me to in a number dot 3 or 4 decimal places. I assure you that this process is possible, so if you get a negative answer, you have done it incorrectly. Okay? That's what I have for you today. I hope that this is helpful for you. I hope that working along with me is helpful for you, but give me feedback into the muddiest points, anything about this lecture, anything about how we're doing things, so I can work on trying to make it the best for you that I can where you are. I hope you all are well. Happy Friday. It's the weekend, which means nothing to me. It's all the same day over and over again here in the Wanklin household. But enjoy the time that you have, and hopefully get outside and breathe some air, or just shout at your neighbors about thermodynamics. That'll be a good thing. Make sure you're 6 to 13 feet away and just shout at them and tell them what you know. Okay? But don't do it obnoxiously. Just do it out of kindness. Whatever. Yeah, it's time for me to shut up and get ready. I will talk to you later.